Could you do me the favor again?
Yeah. When I win the Powerball, I'm going to buy ACs for this one. Working quiet ACs. You're going to have a tiny wall for yourself instead of the cameras.
Okay, so this one here is the slide. Yeah. I explained to you last time how the conversion of a string of digits to a number works internally. Conveniently, there is a function that does that for you. That function is called a to I. I'm on slide 29 in case you want to catch up to it. That function a to I, A is short for ASCII, I is short for integer. So it turns an ASCII string that consists of digits only to the corresponding integer that it represents.
Does the a2i work on other stuff besides C strings?
No. A to I works on C strings only. In particular, if the C string that you feed it does not start with a digit, then the value that it returns is 0. So if, for example, like you have on the slide, you call a to I with a string that has a hash mark as the first symbol, then that hash mark is in the digit, and so therefore none of that string is further processed, and it stops right before the first character, and it just returns 0. On some systems, there is a difference between long and int. So on those systems, if you actually want to ensure that the return value is a long, then you would use a to L instead of a to I. There's also a to F. F here stands for floating point. So you can feed that C string that consists of a number with decimals, for example 9.99, and it will convert that to a double. It will also read scientific notation, for example 1.23 e minus 6, something like that. And again, if the string that you pass in as an argument, if that string does not start with something that is a legal character for a floating point value to start with, for example a plus, a minus, a digit, a period, if it doesn't start with any of that, then it returns 0.0. Like for example in this case here where we call it with $9.99, well, the dollar is not anything that can occur in a floating point number, and so therefore the conversion stops right away, and 0.0 is the result. Yeah, cstdlib is the header file that you need to include if you want to use the conversion functions a to I, a to L, or a to F. cstdlib. Okay, now for the purpose of illustrating how to combine these ideas, we're going to look at designing our own numeric input. So there's a function that we're going to look at in display A2 that's called read and clean. It reads a line of input. It discards all the characters other than the digits, just silently weeds them out. So if there's spaces in between or anything, they just get dropped. And then it calls a to I to convert the cleaned up C string to an integer. So yeah, here you see the function prototype. It has a call by reference parameter that we will set to the result, and we call it here in the lower third of the slide. And on the next slide you see the function definition for read and clean. It tries to get a character that sets an index to 0. If the character that we just obtained is different from the new line, then we check, then we go into this loop and we check, was it a digit? If it was a digit and our index is less than array size -1, has to be less than array size -1 because we want to keep that 1 for the \0 that we need to add on to the end. And remember, the last position in the array is array size -1. So that position at least we need to reserve for the \0. So if that is the case, if it's a digit and we still have space in the array, then we set the current index position of that array to this character that we just read, and we increment the index to point to the next position in the array, and we get the next character, and that repeats until either we run into a new line or we have exhausted all the space in our digit string array. Once we leave from the loop, we force the next position in the digit string array to have that \0, and then we call a to I with digit string and set n, the call by reference parameter of this function, to the result. Is that clear? Are there any doubts? Okay, so next, well, remain seated because we're going to have another source code to look at. So now we're using this again as an example of how to apply these things that we discussed earlier. We're going to use this for confirming input. So a function getInt is what we're going to look at, that uses the function read and clean to read the user's input, and then it verifies with the user, this is what I got from your input. Is that really what you wanted me to use? And yes, no. Yes, Sebastian?
A to I, A to L, and
A to F.
What was that again?
A to I is ASCII to integer. That's taking
okay.
a string of digits
Yes.
and converting them to an integer value. A to L, the same for long instead of int. And A to F if you have floating point, if you have decimal points in there. Okay, so this function here on the display A3, it uses a function newline that we have discussed previously. It uses this function getInt, and the function getInt here uses the function read and clean. And getInt has a do-while loop. It prompts the user to enter the input, then calls this function read and clean, which reads digits and drops everything that's not a digit, and sets input number to the value obtained in this way, and then our getInt function asks the user whether this is what the user really wanted to enter, and if the user responds with a Y, then it leaves the loop, and if the user responds with anything but a lowercase or uppercase y, then it continues the loop. So the way this function might run is here on slide 82. If the user enters something like $77*5XA, then the program will say you entered 775. Is that correct? Yes, no. And the user has a chance to enter an answer to that, and so on. Eventually, hopefully, the user is successful in entering the number that he or she actually wants to enter. Okay. The first bullet point here asks you whether you can describe the benefits of reading numeric data as characters before converting the characters to numbers. I think that's maybe a bit it asks more for an opinion, I would say. So one could argue that the benefit is that you have full control over the conversion process, and you can design, like what we did now, presumably such an input method for a very noisy environment where whatever people are trying to use a mobile phone screen with huge gloves somewhere in the Arctic or something like that, and they just can't hit the keys on the display right, something like that, whatever. I mean, I think it's a bit contrived. Anyway, you think you can do input and output program? Can you write code that does input and output with C strings? Do you think you know how to do that? Can you use the extraction operation with C strings? Did we talk about that yesterday? Yes, you can. How about the insertion operation? That too, exactly. Yes, exactly. And of course, you can also get individual characters and build up a C string character by character. Yeah. So do you think you know how to use A to I, A to L, and A to F? Yeah. Okay. And the last one, that's a difficult one. Which character ends a C string? Yes. Okay. Good job. Yeah. Okay. Before I continue with the next section, are there any doubts? Anything that you would like to clarify some more? Not at this point. Okay. Okay. So remember, during yesterday's lecture, I repeatedly said, okay, here's a piece of bad news, and here's a piece of bad news, and here's a piece of bad news. This looks more ugly than we would like, and so on and so forth. Now, today, you will get a lot of good news. Because with the string class, all these things that are bad news when we talk about C strings are good news because we have all the convenience here. So you will see that we have, for example, comparison just by the regular comparison operators and stuff like that. Okay. The reason why we have both, the reason why we have C strings and why we have the string class is a historical one. If we would design C++ from scratch, then we might not have the C strings. But since C++ is an extension of C, so whatever was a legal C program also has to be a legal C++ program. And therefore, it's necessary to have this same way of dealing with strings that we had in C before C++ was invented. And that's why we have both ways. Okay. The string class allows the programmer to work with strings much more conveniently. For example, you can just create a string by saying string, let's say name. Like you declare any other not any other, but variables like integers or booleans or double values. You just, instead of int or double, you just say string and then the name of the variable. No need to specify a size. That's already interesting. No need to specify a size. So how large is that string going to be? As large as it needs to be. Yeah? So you assign something to it, and if it wasn't large enough beforehand, then under the hood, it grows the space to be large enough to accommodate whatever you want to store in it. That's the good news. There will be a little bit of bad news too, but we'll get to So you need to include string if you want to use strings. Many of you have already worked with strings. So you will know that. So you need to include string, and that brings in this class string. String is a class, and you can then use that class in object declarations like this one. Okay. If you have, on slide 38, if you have three strings, let's say, called S1, S2, and S3, then you can write something like S3 is assigned the value of S2. Remember, when we wanted to do that with C strings, we had to use strcpy, and that function had a whole list of problems, right? Things to watch out for, dangerous bends, possibilities to make mistakes. Yes, all that. Well, here, all that is taken care of. If the string S3 isn't large enough to hold all the characters that are in S2 right now, well, as part of the assignment internally, it is made larger. Yeah? Obviously, that entails some overhead. Yeah? I mean, that should be clear. If every time I do an assignment, there has to be a check, is the target large enough to hold the string, even if we know for sure that it must be large enough, well, then that's an overhead in comparison to the C strings. I still recommend that you use the strings because it's very unlikely that anytime soon you will write programs that are so time critical that you need to tune them to this last little bit of, get the last little bit of performance out of them. Very unlikely that you will run into that anytime soon. So I recommend that for the sake of getting the program right, instead of getting the program to run fast, you use the string class. That makes it easier to get it right. You can work with strings and C strings together, like here. Whatever. Have an interesting name to put here. Okay, well then it's double tag. Okay, so this here is a string object. This here is a C string literal constant. But they work together. I can use the C string literal constant to initialize this string object from. Yeah? I can also write something like this. String name1 is initialized from name. Now I'm using the same symbol. I'm having a string object here, and I'm having a string object here from which I initialize. So what you see here is overloading at work. The initialization here is overloaded. It's using an overloaded operator that has one definition when you use it with a string object on the left-hand side and a C string literal constant on the right-hand side, and it has a different implementation when you use it with string objects on both sides.
So
Yes?
what if you put a backslash 0 behind the whole top?
You don't have to,
I know
because
you don't, but if you do,
if you would, then it would have two backslash zeros at its end, right? If I put a backslash 0 here, then this C string literal will actually have the D, O, N, A, and so on up to the K, then a backslash 0, and then because I've put it in double quotes, there's another \0 that gets added to the end, because that's what the double quotes mean. The double quotes mean a literal string constant that is ended by a \0 without me having to write that \0, right? Okay. There is a nice shorthand for concatenation. That's just the plus sign. So if I want to concatenate one string with another and store the result in a third, then I can just write S3 becomes S1 plus S2. And what happens is that S2 is concatenated onto S1, and the result is stored in S3. And again, if there isn't enough space in S3 at the beginning of this operation, then it grows to have enough space. So all these problems that we had with strcit, all those problems are hidden away from us. They're gone. Yeah. There's another way of initializing a string object. That's by writing it like this, like you have on the slide. Basically, this is the same as saying string noun is initialized with the equal sign and then to the string adds. It's just a different notation for that. The concept that is at work here is the concept of a constructor. I think I mentioned that maybe once or twice already, but we didn't really talk about it in detail. A constructor is a function that every class provides. And the purpose of a constructor is to set up the state of an object so that your program can start working with it. Yeah? To have one defined initial state for all the objects that are constructed from a certain class. The default constructor is a constructor that does not take any arguments. So the default constructor would not have an argument here, and it can be used by just not putting anything there. By not putting any parentheses here and not putting any argument there, I'm using the default constructor. And the default constructor for the string class is to generate an empty string. Yeah? So that every string, when you declare it, every string, if you don't initialize it, it is the empty string, not just some garbage string. And then there are like this constructor here that takes an argument. That's not the default constructor. That's another constructor that the string class offers that can be used to initialize the newly constructed string with these characters. Okay, oh well, this is a slide I'm going to have great fun with. I don't like it. I'm glad I didn't write it. So I said that you can mix C strings and strings, string objects and C strings, and you can, as you see here, we have this assignment string phrase is initialized from, and then I love plus adjective plus a space plus a noun plus an exclamation mark. And then it says it is not so easy for C++, and that's I mean, every C++ compiler will accept this. So apparently it's easy for C++. Every C++ compiler I asked didn't have a problem with it. So anyway, but I mean, stop the ridicule and talk about what goes on here. So what we have is we have an overloaded concatenation operation. This concatenation operation, the first one here, uses the concatenation of a C string and a string object. So we have plus that takes a C string and a string object and produces a string object. That's this plus here. Then this plus here, well, by the time we want to perform this concatenation, we have a string object from the first concatenation as a result of the first concatenation. So we have a string object plus a C string. So we need another overloaded plus symbol that takes a string as the first argument, a C string as its second argument, and it produces a string. So by the time we've done that, we have a string here, and then we concatenate that with another string. So we need yet another version of that concatenation that takes two string objects and produces a string. And then last not least, we have another concatenation, and that takes a string and a C string, which we already have here. Yeah, so we have three different versions of the plus. This one here is that. This one here is that. This one here is that. And this one here is that again. Yeah. Okay. So that's the overloading that takes place. Salud. The insertion operation can be used with C strings. We've seen that. It can, of course, also be used with string objects. The extraction operation can also be used with string objects. That should not be surprising. Always remember that the extraction skips leading whitespace and uses whitespace to end the input. Okay, now to make things really confusing, there is another getLine function. Remember, we already talked about a getLine function. That getLine function we talked about was a member function of the input streams, and we passed to it two arguments when we called it. We passed as a first argument a C string where we wanted to store the result, and as the second argument the length, the declared size of that C string. Now, there is the other getLine function that we're going to talk about now is not a member function of the input streams. Instead, it is like a standalone function. It's not used as a member function. It's used like exit, for example, like a standalone function, not with a dot something. And you pass as the first argument the stream from which you want to get something, from which you want to get the line, and as a second argument you pass the string object into which the line is to be placed. Now, what's confusing about this is that the strings are the more object-oriented implementation. If you think about C strings and strings, the string class is the more object-oriented implementation. But the getLine function that you use with the C strings uses this member function syntax on the input streams, which is the more object-oriented way of expressing it. So with the less object-oriented implementation of the strings, you use the more object-oriented way of calling getLine, whereas with the more object-oriented, yeah, so you see what I'm saying. So that's a bit confusing. This slide 44, illustrates how you would use getLine, for example, to get an entire line from cin. So it's just to call getLine cin line, and we don't have to specify a size because the string object can grow to as many characters as needed. Let's look at this display 8.5. There you will see how you can work with strings and getLine. So the program prompts the user for the first name and the last name, and then it outputs this record name. The record name is generated by putting the last name first, then putting a comma and a space, and then putting the first name. And then the program tells the user about this record name, and then it outputs a motto, and it asks the user to enter a new motto, and then the program outputs our new motto will be, and then that motto. So that's just to show you how you can work with concatenation, with the extraction operations into string objects, with the getLine function, and with the insertion of string objects. The getLine function is overloaded. There is another version of it that takes 3 arguments when you call it. There, the third argument is the delimiter character. If you only supply 2 arguments in the call, then by default the new line is used as the delimiter, as the line end symbol. And if you do supply a special character that you want to use for ending the input, then you can do so. For example, here on that slide 46, you see the question mark being used for that. Skip this slide 47, also the slide 48. Okay, I'm going to continue with 49. Again, when you combine the extraction operation and the getLine, there might be some unforeseen things happening. You have to understand how the extraction operation and the getLine, how they work precisely in order to know where this comes from. It's actually not that hard to understand. It's just something that you have to keep in mind. When you use extraction and the input that the user enters ends with a new line, then remember what the extraction does. The white space ends the input, but then the putback member function is used on the input stream, and the character that did end the input is put back into the input. So when a new line ends an input, that new line is still in the input after the extraction operation. If you call a getLine function immediately afterwards, that getLine function reads up to the next new line character. Well, that's just going to be the first character that's still in the input. So you will get an empty line. Yeah? So let's think about this a little more. Imagine you enter a word like hi, and then you enter the new line. The H and the I go into some string into which you extract. So we're assuming you're using the extraction operation. The new line is red, but then it's seen that it's a white space character, so it's not made part of the string that was extracted. Instead, it's put back into the input. So now our input pointer, so to speak, stands right on this new line character. Now if you call getLine, what is it going to do? It's going to read up to the next new line. Well, that's just the next character. So it's just going to extract or get you an empty line. Yeah. So the remedy is to use something that we did before, call a function like the function newLine that flushed everything in the input until the next newLine character, including the next newLine character, so that everything is set up to get the next line. There's another way to accomplish the same thing. It's called, the member function is called ignore, and you can pass two arguments to it. The first one is how many characters at most you want to drop from the input, and the next one is the character that you're actually looking to drop. So if you say ignore 1000 comma and the \n, then you're dropping until the next \n, but you're not dropping more than 1000 characters. Okay, some more good news about strings. Strings allow you to perform the indexing operation. Just like you had the indexing operation on C strings, on strings, I can also use this indexing operation with the same syntax, the square brackets and an index position. What goes on inside is a little more complicated than what goes on when we use indexing on the C strings. I'm not going to go into it right now, but the syntax is the same, and I'm going to get the ith character that would appear in the ith position of a printout of that string. As for C strings, the index values are not checked for whether they are within the bounds of the array, so you don't get an out of bounds warning or error or anything like that. If you are accessing a position outside of the length of the string, then that's your responsibility, and it's undefined what happens to your program. Let's check that display. No, we don't really need to talk about that. So let's go to slide 52. Another convenient function is the length function. That is to determine the length of a string, obviously. The number of characters that the string currently holds. Yeah?
It reads the length and outputs it.
It what?
It reads the length and it outputs it.
It returns it. You call the function, and the value of that expression will be the number of characters that are currently in the string. Well, there is a similar function also for the C strings called strlen. Yeah. I'm not going to talk about that. Okay, more good news. If you want to compare two string objects, you can do so just with the comparison operators. For example, the double equal sign, as you see here on slide 54, the double equal sign returns true if two strings have exactly the same characters in them. Exactly the same. Meaning there is a difference between uppercase and lowercase. and you have the less than, the greater than, the less equal, the greater equal, the not equal. You have all these comparison operations available with strings, and the underlying order that's used here is the dictionary ordering that you would, or the phone book ordering, whatever you want to call it. The proper term is lexicographic ordering. Okay, and now for some fun, we're going to look at a program that does palindrome testing. Who of you has never heard the term palindrome before? Okay. A palindrome is a word or a sentence that reads the same forwards and backwards. And I happen to find them very entertaining. I don't know. I think it's just a thing of beauty. A good palindrome, in my opinion, is a thing of beauty. The one that you see here on the slide that is one of my favorites is a man, a plan, a canal, Panama. If you read it backwards, you can see a man, a plan, a canal, Panama. So, what we want now is we want a program that will test whether the input of a user, the input that the user makes, is a palindrome or not. And if you read an entire sentence like this one, that might seem very challenging at first, but if you break it down into individual steps, like if you identify what you do when you check this for palindromes, and break that down into individual steps, then it's not that difficult at all. I mean, what's obvious is that we don't care about capitalization. So one thing that we might do to the input is just to normalize it to one case. Make it all caps or make it all lowercase. It doesn't really matter because we're just going to use that representation internally in the program. So it doesn't really matter which we choose, but by normalizing it, we make our work easier, because then we just have to compare for equality and not take the different casing into account. And also, we don't care about spaces, commas, apostrophes, exclamation marks, none of those. So we just drop everything that's not a character. Or better yet, we have a list of stuff that we want to remove. So, one function that we're going to have is called remove punct, for remove punctuation symbols. Actually, it also removes white space. It removes all the characters that we're not interested in. So, remove punct compares each character in the string to the characters in a string containing unwanted or uninteresting symbols. Yeah? Symbols that we want to weed out. And when the current symbol in the original string is found in that list, well, then it doesn't go to the output. And when it's not found in that list, well, then it's a character we're interested in and it does go to the output. The output is this string no punct. That's where we collect all the characters of interest that remain. This is a little technical here. There is a function substr, which substr is short for substring, and it can take a string starting at a certain position for a given length from a string. Yeah? So you can take a substring from within a string. You can say, from this string, give me the string starting at position 3 of length 5 as a string. yeah, as I said, it's a little technical what we're doing here. There's this variable HR that our implementation is going to use. And this HR, we want that to be a string. But we want, I mean, the data type string. But it only needs to be 1 character long. So we're going to use the substring function to extract a string of length 1 starting at a given position. And we're not going to use a char because the people who wrote the slides wanted to illustrate this function substring. The function find that we use also inside the function remove punct to check whether the string HR is actually in the list of symbols to remove. That function find is overloaded, and there is also a version that would take a single char. So it's not strictly necessary to do it this way. I think the only reason why it's done that way on the slides is because the people wanted to show how to use the function substring. In my opinion, it's a little more complicated than it needs to be. Okay, let's go through this display here on slide 88. There is a swap function. We've previously talked about that. There is a reverse function. It returns a copy of S, but with the characters in reverse order. There's our function remove punct. We're going to look at it in a moment. And there's a function called make lower that makes all characters lowercase. And then, of course, there's this the central high-level function isPal that actually returns true if it is a palindrome and false if not. So our main function just gets input from the user, an entire line of input, and then calls the function isPal on that input. If that isPal returns true, it outputs the entire string of input, and it says, yes, that's a palindrome, and otherwise does the same, but says it's not a palindrome. So swap is an old hat. Reverses a string. Now that's worth talking about because I think it can be improved. So the reverse function that we have here looks like this. Const string reference.
Professor, I have an appointment in 2 minutes, right? See you.
Okay, so the way it starts is that it initializes start to 0 and end to s.length. And then it has this while loop. Oh, it has a string temp. And in the loop, we decrement end. Then we swap. Oops, that should be the same. We swap. Oh, okay. Missed one thing. The S here. We swap temp at position start with temp at position end. And then we increment start. And then there's the return temp. That's not really that important. So why is this not as good as it could be? If you look at start and end, we have two index positions. And these index positions have a slightly different meaning, unfortunately. Because end is initialized to s.length. So end initially holds an index position that is outside of the bounds. So end at this point, if I look at the state of the program at this point, then start at this point will be the index of the first character that needs to be swapped, but end will be one more than the last character that needs to be swapped. Do you see what I'm saying? Because end is initialized to s.length, end is one more than the highest possible index. Yeah? So it's one more than the index of the last character in the string. So the semantics, the meaning or the purpose of these variables is slightly different. They're very much alike. They're both indices into the string, but they're slightly off because one always gives us the position where the next character comes from, and one always gives us the position one more than the last character where a character comes from to be swapped. That's bad design because it forces the programmer to always remember which kind of indexing is used for which of the indices. There's basically two different kinds of indices we're using here. Do you see that what I'm saying? Yeah. That's a recipe for confusion. So, and as you can see here, it forces us to decrement end before we do the swap, but to increment start after we've done the swap. Again, that looks weird, right? So how can we improve it? Well, for one thing, we can subtract one here when we initialize end. And then now, at this point, we have that both start and end are the positions where the next characters to be swapped come from. And so therefore, before we do the swap, we do not need to decrement end, but we need to do it afterwards. And now the treatment, and as of course within these curly braces, and now the treatment of start and end is more uniform. Yeah? And so that's better design. Let's see if this is still true. We might have to say, while start is less than end, we want to do that. If start becomes equal to end, we don't need to do that anymore. Right. That condition is still okay. Because we have this uniform treatment, we might even want to go a step further and incorporate the increment and the decrement into the function call. Then we get rid of these two lines and we no longer need the curly braces because we only have a single statement inside the loop. And I think that is a better way of writing it. Okay. Any questions about this? Any doubts? Comments? Anything you'd like me to go over again?
What does it s.length do specifically?
S.length.
Yeah.
S is the string object that we get as a parameter here. And s.length is the member function length on the strings. That gives me the number of characters that are currently in the string. Another thing that we've talked about const array parameters, but we haven't talked about const reference, call by reference parameters yet. A const call by reference parameter, in a way, is similar to a const array parameter. While it does pass the arguments. So it only creates an alias to, S is an alias to the argument that will be used in the function call, but the function is forbidden from changing the any of the characters in this string. Yeah? What is the benefit of that? Well, a string can be a rather large object. A string could consist of thousands, hundreds of thousands of characters. And if we would not pass it by reference, but we would pass it by value, then a new string would have to be created when a function call happens. And all the characters in the argument string would have to be copied over to that new string. Yeah, so that is, that's a lot of copying, and that's not really necessary here, because we create this temp string here that we initialize from S. So there's no point in having an entire copy in S and then making temp a copy of that copy to work with. Okay, that's the reverse function. The make lower function, oops, didn't want that. The make lower function here is just a loop that goes over every character in the string and replaces it with the to lower of that character. Basically, that's what it does. So, and now the most interesting function here is the remove punct. The remove punct has a string as its first parameter, and it has another string called punct as its second parameter. So this second parameter called punct acts as a list of symbols that we want to remove from the string that we get as a first character. Sebastian, you have a question? Okay. So this string no punct is going to be where we collect the result, and yeah, s underscore length and punct underscore length are just variables where we store the length and the length of the original string and of the punctuation symbol string. They wouldn't strictly be necessary. We could also use s dot length as a function call here, and use where is it? Punct dot length as with a member function call here. Okay, now we get to this loop where we loop over all the characters in the S string, and we extract from S the one character long substring that starts at position I. So for every position in the original string, we extract a one character long substring and assign it to the string HR, and then we call the member function find, supplying this HR and starting at position 0 in the list punct, in the string punct, to find does a char occur somewhere in the list punct. Does this HR that we just extracted, does this occur somewhere in the list of our punctuation symbols? And this find member function will return a position. And that position is going to be within, in between, well, including 0 up to but less than punct length. And so we know if we get a location back that's either less than 0 or it is greater or equal to the length of that punct string, then we know it wasn't found. And if it wasn't found, well, then it's one of those characters that we're interested in, and we have to add it onto the end of our string no punct that we're creating. And if it was found, well then we don't need to do anything because we're not interested in that symbol, and we can just silently ignore it and go on with the next symbol. Yeah? So anybody have any doubt about this? This is all clear?
Yeah.
That's good. Okay, then let's go back to this here. Yeah. I told you that we can often use C-strings and string objects together. For example, when we wanted to initialize a string object, we could use a C-string literal to do so. And there was, so to speak, an automatic conversion going on from this C-string literal to the string object. The other way around, it's not so easy. By the way, I'm on slide 59. I cannot use a C-string to assign a string to. So if I have a string object, I cannot just assign that to a C-string. At least not just with the assignment operator. And neither can I use strcpy, string copy, to copy the content of a string object into a C-string. Because strcpy only works with C-strings as a target and C-strings as a source. So in order to remedy this, there is a member function called c_str, and that gives you a C-string with the characters of the string object in it. Yeah? So if you have a function that needs a C-string, but you only have a string object, then you can use that string object, member function .cstr, and that gives you a C-string that holds all the characters of the string object. And then you can process it with a function that expects a C-string. Any doubts about that? So, for example, the member function open for the input file streams expects a C-string. Now, if we assume that you don't have a C-string, but you have a string instead, so let's say your program looks like this. You have a string, file name, and then, of course, you have some include files and something up there. String file name, and then you have asked the user, you've prompted the user to enter a file name, and you have obtained the file name from the user. And now you want to call the member function open with some input file stream. Let's say. But file name is a string, so you cannot do this. You cannot just do an in.open file name. Does not work. But what you can do is you can do filename.cstr, there's an underscore in there, c_str. That does work. That is okay.
Why does the other one not? Why does the other one not work? C?
Well, because the function open expects a C string. So you need to have a C string here. Actually, this might be a bad example. Come to think of it, it might be a bad example.
Que con los últimos slides nosotros podemos hacer exactamente eso.
Yes, but we didn't have a string file name. We had a char array, and so we had a C string. But come to think of it, open might actually be overloaded so that it'll take a string object also. Check that quickly. Might have been a bad example. Yeah, as I imagined. Yeah, sure. Okay, so this with the open was a bad example because it actually would work because open is overloaded. So there's one version that works with C strings and there's another version that works with string objects.
So it works either way.
It works either way. Yeah, it was a bad example.
That's good to
It was a bad example. But there are, of course, functions that do require you to provide a C string. And for that purpose, you have this function. Okay. How about the second one? Who of you thinks that you know how to write code that reads an entire line into a string object? It's a single line of code that you need.
Thanks.
An entire line of code into a string object, not into a C string. So, Gabriel, how would you do it?
I'll declare a string called line.
Okay. And then?
Is it an entire line, right? So
An entire line.
Write get line. Open parenthesis, sin, and then line.
Yeah, exactly. That's it. Does it. Okay. The next one, no. Yeah. Okay. Yeah, these are this. Okay. So that concludes the section on strings, and we're going to continue talking about vectors next. There's a relationship between vectors and arrays, and C strings and string objects. Let me talk about it. So, the C strings are implemented as arrays of characters. And strings are implemented somehow, opaquely. We don't really know how. It's not transparent. We don't see how they're implemented. They might be implemented in many different ways. But what the key feature is that we can add elements onto a string, and the string will grow if it hasn't enough storage space to hold all the characters. Well, it's similar, or the general concept is captured in array and vector. C strings are arrays of characters, so arrays of a specific base type. Arrays in general can hold any type as the element type. Well, the same is true for vectors. Vectors can hold any type, and you can think of strings as being vectors of char. So they're a special kind of vector. They're a vector where the elements have to be characters. But there's the more general concept of a vector. And a vector could hold integers or doubles or input file streams or whatever. The key feature of the vector is that it can grow in size. That you don't have to settle on a declared size when you write the program. In that sense, the array and the vector are at two ends of a spectrum of between static and dynamic. Yeah, the arrays are static in the sense that you have to decide on the size of the array when you write the program. Before you compile it, you fix the size. The vectors, on the other hand, allow you to defer that decision on the size to as long as you want, basically, because as the program runs, you can always add more elements onto the vector, and so you don't ever have to settle on one specific size. You can always add more elements onto it. So the size of a vector is dynamic, and the size of an array is static. Okay. So in that sense, vectors are like arrays that can change the size as your program runs. Vectors also have a base type, but vectors are implemented as templates, and we've never spoken about templates before, so if you don't recognize that term, don't worry, you didn't miss anything. We didn't talk about it yet. A vector is created like this. And here in these French quotes, this or the angular brackets or whatever you want to call them, this int here, that is the base type. That is the type of the elements. And vector itself is a template. And for now, I'm going to explain a template just as like a template for a class. It's not really a class because there's some holes in it. Yeah, in order to really make it the source code for a class, we have to fill in a few holes. That's a template. And then when I fill in the holes, it becomes a class. And in the case of the vector template, the holes are where the data type of the elements goes. So by supplying this int here, I'm filling this template, and I'm putting an int into those holes in the template, and that makes it a class, and then we can use it here. Now that seems to be a bit far-reaching. Don't worry about it. That is something that you really only have to understand in the next semester. Yeah, it's not essential for this course. Okay, so we can form vectors with any base type. In particular, we can have vector of double, for example, whatever. Let's say this one. But as I said, anything is legal here, not just primitive types. Even class types could be used here. For example, a vector of input file streams is possible. Or better yet, a vector of vectors of int. That is possible too. Whatever, dvec. Yeah, a vector of vectors of int. Now what does that mean? It means that I have a dynamic structure, a dynamic list, so to speak, that can grow, and the elements of that list are vectors of integers. Every such element, in turn, is a list of integers that can grow.
It's a list of lists.
Yeah.
Why did we learn arrays
Hmm?
if we could just use vectors?
Why do you want to use an array if you could just use vectors? Good question. It's a good question, yeah. For most applications, I suggest using the vector. Just like I suggest using the string class for most applications where you need strings. In favor of, use the string class over the C strings. And here, use the vectors over the arrays. Why? Well, because it's more convenient to work with the vectors. And now you might ask, well, why did I learn about arrays in the first place? Well, because when we talk about arrays, it's very clear. There's a direct explanation as to how they're implemented in memory. So that's good to understand how arrays work, because we can always say, well, internally this is what goes on. How are vectors implemented? Actually, one library might implement them in one way, another library might implement them in a different way. That's up to the implementer of the library. We only have guarantees as to how they operate, not what they do inside. Only as to like pre and post conditions, what we can assume these operations do. But there's no transparency as to how this has to be implemented.
So depending on the include files, the vector will work differently?
No, but depending on the compiler that you're using, or depending on the platform on which you are, it might be implemented differently. But the interface and the behavior that you can observe as a programmer is going to be the same. When you use, for example, the indexing operation and you want to get the 15th character, you're going to get the 15th character no matter what implementation. Yeah? Okay. You can use the indexing operation with the square brackets. I'm on 64. And you can use that indexing operation also to overwrite an element in the vector, but only if that element already exists. If you have just created a vector like here, then that vector, just like the strings, when you just create a string and you don't initialize it with anything, then that vector is initially empty. Then you cannot say something like this. Yeah, that will not work. Why will it not work? Well, because it's undefined what is at index position 15. Or better yet, indexing into the vector at index position 15 is undefined. Because that vector is currently empty. So it doesn't have an element at position 1 or at position 0 or at position 15.
Garbage value.
No, it doesn't even have a garbage value. The internal structure of the vector is not set up so that indexing into index 15 would work correctly. So if you try to index into position 15, what happens is undefined. You might have a crash of the program, or it might just store the value somewhere in memory. Yeah? So this is no good. You have to first ensure that there are elements. And in order to generate elements, there is the function pushback. That's one of the ways how you create new vector elements. The function pushback, the member function pushback. It creates a new vector element at the end of the elements that currently are in the vector. So if you start with an empty vector and you do the first pushback, you have created the first element. That's the element at position 0, at index position 0. So if you have done one pushback and only one pushback, then the only index position that you can legally use, or that's actually defined, is indexing into position 0. Square bracket 0, that index. Square bracket 1 would not yet be defined. Yeah, so with these three pushbacks that we see here on the slide, we would have a vector that has 0.0 in position 0, 1.1 in position 1, and 2.2 in position 2.
That would be the vector size.
Just like we have the function, the member function length, to get the number of elements that are in a string, we also have the member function size to get the number of elements in a vector. Yeah. So size tells you how many elements are currently in the vector. If you want to iterate over all the elements in the vector, there are several ways to do it. You can do it with what is called iterators, which we are not going to talk about in this semester. That's something for the follow-on course. One way to do it is to go over all the index positions from 0 up to the size of the vector, but not including the size of the vector. One element less than the size of the vector is going to be the highest index position that we can use. Yeah. Size actually returns an unsigned int. That is something I think I mentioned it once. An unsigned int. Remember when we talked about the integers, I told you that we have a total of about 4 billion values if we assume 32-bit integers, and about 2 billion go to the negative and 2 billion go to the positive. Well, in some applications we don't need negative values. For example, when we want to talk about sizes of vectors, well, the smallest size that a vector can have is 0, not -1, right? There's no need for negative values here. By saying that we want to use all the 32 bits for non-negative values, we end up having 4 billion different numbers in the positive, in the non-negative. I mean 0 and up to about 4 billion. Yeah? So if we would use int as the return type of size, then we could have sizes of at most 2 billion, and since we use unsigned int for that, we can have sizes up to around 4 billion. Again, always assuming that we're talking about 32-bit integers. Okay, so this loop that you see here on slide 67, that is one one programming idiom for going over all the elements that are currently in a vector. There is an alternative constructor. Remember what I told you about constructors? If you have a class type that you use, then there is always a constructor, and the default constructor for the strings was to initialize that string to an empty string, and then there was an alternative constructor where we could supply an initial string with which that string would be initialized. For the vectors, the situation is similar but not identical. We have, for example, vector int v. The default constructor, if I don't put anything there, is the constructor that creates an empty vector. And if I use an alternate constructor that takes a single argument, an integer, then that's the number of elements I want this vector to have initially. Yeah? So I'm saying I want a vector of integers that starts out having 10 elements already. So that saves me the effort of having to do 10 pushbacks right after creating the vector. Yeah? So I don't have to declare the vector and then have 10 pushbacks that all push back a 0. The value that these elements are initialized to is the 0 of the base type. So if I have vectors of int, I will have an integer 0 in there. If I have vectors of double, I will have 0.0 in there. and so on and so forth. And I don't want to blow your mind, so I'm going to leave that for a little later. As soon as we do that, as soon as we do this here, if we then would have an instruction that outputs the size of v, we would get 10 in the output. Yeah? So that creates a vector and it has the same effect as doing 10 pushbacks, and the size of that vector would then be 10. So here we would get 10 in the output if we would write that. Also, of course, immediately after that, I could do something like this. Yeah? Of course, right after declaring a vector v and saying that it must have a size of 10, we have those 10 elements in there, and that means I'm now allowed to index, for example, into position 12, into position 7, to assign 12 to it. Yeah, because the positions from 0, the index positions from 0 up to 9 are then defined. And I didn't mention this explicitly, but just because I said that the vector should have 10 elements initially does not prohibit me from adding more elements by using pushback. I can do another pushback to have an 11th and a 12th and so on and so forth element. I can do pushbacks as I please. Yeah, okay. So now it's time to mention what I said I was going to spare you with for a moment. The elements that I created when you use this form here of creating a vector, the elements that I created use the 0 of the base type. But what if we do something like this? Vector string v1, and let's call it names. Okay, so here we have a vector of strings. It's called names and has 100 elements initially. When we have a primitive type here, like int or double, it's the 0 of the base type that's used for initializing these elements. Now we have elements that are strings. They don't have a 0, right, in that sense. But what happens is that if you have classes here as the base type of the elements of the vector elements, and you're saying that the vector should have a certain number of elements initially, then these elements are initialized with a default constructor of that class.
So it would be just a bunch of empty strings.
Yes, exactly. Exactly. You nailed it. In this case, it would be a list of empty strings. Exactly. Okay, if you want to use vector, you have to include vector. So, that figures. And what do we have on that display here? Okay, yeah, let's look at this display 8.9, slide 92. There you see all these things with a vector in one little program combined. Up there is the declaration of the vector. Then we tell the user what to do. We get some input from the user. as long as what the user has entered is positive, we push it to the back of the vector, and we output that it was added and what the new size of the vector is, and then the loop attempts to get the next item of data, and so on. It continues until eventually the user enters something that's a 0 or negative, which will stop the loop, and then the program outputs you entered, and has this loop here that goes over all the elements of the vector, outputting each one. And that's that. Yeah, and when the program runs, you can see the user here enters 2468 and a -1, and then the program outputs 2 added, size is now 1, 4 added, size now 2, and so on. And eventually, at the end of the loop, it outputs all the elements of the vector again. Okay. So there are a few problems also with vectors. Still, I recommend to use the vectors rather than the arrays. One of the issues is if you use the square bracket notation like here to set a value at a position that doesn't exist yet, where there isn't an element yet, like for example in this case, then the behavior is undefined. It might be that you get a runtime error. It might be that it seems to run, but something has gone wrong. Yeah. So maybe when we talk about pointers, I will explain what it is that could have gone wrong here. I'm not going to explain it today. Oh yeah, and also when you use the assignment operator with vectors, it does an element by element copy. And what that means is that if you have very large vectors, the assignment operation, although it looks so innocent, could be very costly. It could mean it triggers a lot of internal computation. Is that clear? Imagine you have a vector v and a vector s, and now you write v, s is assigned to v. That looks all innocent, right? If you think of v and s as just simple variables, I mean, assigning an integer from one variable to another, that's an operation that's performed, I mean, in almost no time on a monoprocessor. But if that here is 40 million bytes, and then that will become 40 million bytes in length, and we're talking about some substantial memory movement that goes on here, and yeah, it might run longer than you'd expect from just looking at this line here. So that's something to keep in the back of your mind. If you have very large vectors, then a simple assignment like this one here can actually trigger quite an amount of operations on the CPU. Okay. Some words on the efficiency of vectors. So now we're actually going to have to look a little bit into how vectors might be implemented. I'm not saying that they're implemented exactly like that. They might be implemented like that. Growing memory or allocating memory is something that is costly. Yeah? So, I mean, in the extreme, growing the memory that is allocated to some data structure in your program might mean a call to the operating system, the operating system switching from user mode to privileged mode, allocating memory, getting back to user mode, and all that. So that in the extreme, that's what might be involved in allocating memory. It's not always that bad, but memory management in general is a costly operation. So if you do a pushback, of one element, you might need to grow the memory that is allocated to that vector, because previously it didn't have to hold that element, so maybe it just had enough space to hold the elements that were in it. Now you're doing a pushback, and that might be triggering an allocation of extra memory to that vector. What we do not want is we do not want every pushback to trigger a new allocation. So we don't want to grow the memory that is allocated to a vector by only one element when that becomes necessary. Is that clear? Yeah? Because then we would, with every pushback, we would have this overhead of allocating memory to the vector. So, but also, we do not want to waste too much memory, and to strike a balance between that, what is done is that when the vector is initially created, some memory is allocated to it, even though it doesn't store, even though the vector is already is still empty. It already has some memory to store elements in it. Some memory is already allocated to it. And then every time the vector needs to grow, it grows to have twice as much memory available to store elements as before. So if we imagine that a newly created vector would be able to hold 4 elements, let's just say that, then once we have stored the 4 elements in the vector, and it also has a size of 4 elements, and we want to store the 5th element into it, then the memory that's allocated to the vector would be grown to have twice the capacity. So it would grow to 8 elements. Actually, now storing 5 elements. Yeah? And here we would have the capacity, and this would be the size. Yeah? We have stored a 5th element, so now the size of the vector is 5, but it has a memory area allocated to it that's large enough to accommodate 8 elements. And then it goes on, our vector grows some more, eventually has 8 elements in it, and then when we want to store the 9th element into it, well, we can't yet because it has capacity for only 8 elements, so we need to grow it again. And it grows to have a capacity of 16 and will hold 9 elements now. And so forth and so forth. Yeah? What that means is we're wasting at most a little less than half of the capacity. Now, if we just grew the memory that's allocated to the vector, then we're using a little over half of the capacity for actual data. And we have very few allocations in this way. Very few allocations. In order to have a vector that holds 500 million elements, how many times would I have to grow the vector? No, actually not that many. How many times would we have to grow it? Yeah.
20, no, let's see, 32, 64, 128.
About 25. About.
Good guess, actually, yes. 1 million is 10 to the 20th, roundabout. 500 is 2 to the 9th. So that's about 29 here. But we start with 4 already. So 27 times.
Very close.
Yes, very good. Yes. So 27 times. And that's not really that bad if you consider that if you would always do individual pushbacks, you'd, in order to get to that size, you'd have to do 500 million. You'd have to grow the space, the memory space allocated to the vector 500 million times. And now we're doing it in 27 times.
Fair.
Yeah. Okay, that's it for today.